Yes, the aurora borealis. So at the north and south poles, the electromagnetic radiation that gets in, stop talking, creates a beautiful effect. Sometimes you can actually see it. Sometimes it's also called the northern lights. Sometimes you can actually see them as far south as St. Joe, Michigan. I've only seen them this far south really once in my lifetime. Now, if you go to the UP, you can usually see them, and certainly if you go to Canada or Alaska, they're quite beautiful. Hello.
Lucky wants to know if you still have the light bulbs that you screw into the wooden base, because we're trying to make a battery for the elementary school.
Okay.
And
yes. Go down to the physics lab and go into the back room, hang a right, and there should be electricity stuff there, and there are light bulbs. Okay?
Thank you.
Yep. All right, so these get in. By the way, extra credits. This is called the aurora borealis. Who knows? All right. You both get an extra credit point. I should have known. It's probably a.
It's named after me.
It's named after you?
Yeah. No, actually, it's you.
Borealis? I think you get an extra credit point for that. For having a name. And plus I get to enjoy the anger from the rest of the class.
I have a name. I'm not mad.
You have a name? What is it, what scientific principle does it match? So what?
Wait.
Borealis. Borealis.
Oh, I thought you were saying
Go ahead, Perry.
Now, if your name can make it, if your name is now called.
No, it does not. All right. So here's something. Listen, guys. Here's something interesting about the Earth's magnetic field. It hasn't always been like this. It has not always been like this. In fact, depends, 50 to 100,000 years, it's reversed its direction. It has reversed its direction, and that is evident from core samples, because iron is the only naturally magnetized element, and we're going to talk about that in a second. So when we take these core samples, we can look through history, through time, and actually see the magnetic fields and how they were aligned 50,000 years ago, 100,000 years ago, etc. They believe that the swapping of the Earth's magnetic field actually occurs over a pretty long period of time. It's not like, you dig down and then you go, oh, look, on Wednesday it was this way, but on Tuesday, the day before, it was totally reversed. It takes time. We're not exactly sure how much time.
Do you think that's why the poles are lower in Canada and not higher?
They think that, yes, it has something to do with that. And now let's talk a little bit about iron. Iron, I don't have a periodic table, so I should pull one up. You have a periodic table on you, Carrie? Oh, wow. Carrie, you are the man of the hour. Except for I think it's too big. Maybe not. Maybe we can use this. Is there a smaller one? That's okay. If you look at the electrons, the free electrons, in terms of how these elements interact and bond with one another, how many valence electrons in this group? One. How many here? Two. Whoa, we're going to jump over here. 3, 4, 5, 6, 7. And then how the noble gases, have 8 valence electrons, and they don't like to bond, right? They're a little snooty. If you were to look now here in the transition metals, things get a little more complicated, right? So who likes to bond with one another here in this table?
Halogens and alkali metals.
Yes, the 1s and the 7s like to bond, right? To make 8. The 2s and the 6s like to bond. And why is this element important? Yeah, building blocks of life. And carbon is kind of maybe this is not how Lucky teaches it, but now that we know each other well enough, I am going to say it. Carbon's like the slut of the periodic table. It'll bond with anything. I know. So, it's one of the reasons you get all these different configurations, right? Carbon, nitrogen, oxygen, sulfur, you get all those different, and that's the building blocks, right? Carbon does bond with itself, that is correct, Perry. All right. So, now let's look at the metals. These are the D shell, right, chemistry students? These are the D shell electrons, orbitals, if you want to call them. This would be like D1, right?
Yep.
D2, 3, 4, 5, 6, 7, 8, 9, 10. And that would be a full D shell, correct? Iron's kind of right in the middle of this list. 1, 2, 3, 4, 5, 6. So let's look at, there's a lot of ways that we represent the electron configuration. Yep, we're still recording. Do you remember when Lucky did this?
No.
To to represent the shell? Yeah, remember this? So if we look at scandium, right, and then titanium, and then vanadium, and so on, the electrons will fill up their orbitals like this, right? Remember that? Why is it that, how come we don't just get a second one right here? What does that mean? Pauli exclusion principle. Go, Fem, go.
That means like every axis of that orbital has to be filled up once, so for one it can be filled up twice.
That is correct. Why?
Because electrons repel each other, so
Right.
they want to be as far away as possible.
Correct, because of Paula Abdul, right? Opposites attract and likes repel. It was the lesser known verse in the Opposites Attract song. So we'll do this, right? And then once we get up to 1, 2, 3, 4, 5, 6, then what happens to the 6th electron? Yeah, it has to share an orbital, right? And then how do we represent this 6th electron? Yeah, what does that mean? And then we do this and so on. Yeah. Now we're coming back into physics, baby. Those are little half arrows. Isn't that the way Mr. Luckhurst drew them? Or did he make double arrowheads? Oh, so Lucky does them like this? Okay. No, this is actually a legitimate question because I didn't know why you guys thought it was a 7.
I thought it was a L, and I was like, wait.
Well, no, I understand, but does that make more sense now that you see the one with the acute angle? All right. So the reason for this opposite spin has to do with the relationship between electricity and magnetism. Every electron, every moving charge, and this comes from like the sun or atoms or magnets or anything, every moving charge has a little magnetic field that surrounds it, a little tiny one. And when the electrons are close together in an orbital, they spin in the opposite directions because that naturally cancels, and it keeps everything closer to a ground energy state. It keeps the energy as low as possible. If they're spinning together, it's like they're helping each other, and then, woo, it takes a lot of energy, and you create this magnetic field, right? So, the weird thing about iron, which is, if we look at the periodic table, 1, 2, 3, 4, 5, 6 D shell electrons. Here's what iron does. 4, 5 orbitals, and we're going to fill the first and then the second. Sorry, I'll make them more acute. 5, and then it should do that, right? Oh, wait for it. Wait for it. What?
I knew it.
That's a big deal. That one electron has the same spin as its orbital partner. And if they're spinning in the same direction, right? Everybody do it. Spin in the same direction. Do the spin. Do the spin. Thank you. Thank you, Chad. You get an extra credit point for being enthusiastic spinner. Oh, not as enthusiastic. As Matt. Sorry. No. Your last name, what is your last name? The Smith exclusion principle? No, if only your last name was Pauly. All right. Sorry, Matt. Pass that to Matt. Other Matt. All right. This makes iron, babies. This makes iron the only naturally magnetizable element found on the planet. Yep. Now, we can force materials to be magnetized, and we're going to do that later. But this is the only one. You can actually dig up, and I do have a piece somewhere. We'll bring it tomorrow. We're going to play with toys tomorrow. You can actually dig up iron ore out of the ground, and it will, like, lift a paperclip. Okay? So, now let's go back to the Earth's magnetic field. They're not 100% sure why the Earth has a magnetic field, but they believe that it's likely due to the iron content in magma. Magma when it's underground, lava when it's above, right? Yep. And so as that magma flows, moves around in the, both interior and even close to the surface of the Earth, it creates a magnetic field. Now, it's not a super strong magnetic field, but it does the job. It shields us. About every 50 to 100,000 years, when we look back in the geological history, and it's obvious that the Earth's magnetic field has swapped because the magnetic field lines are pointing in different directions, there's been an interesting effect that follows it. As the Earth's magnetic field shifts, it is likely, scientists believe, we don't know for sure, it is likely that we lose some of this protection. And so if we lose that protection, the Earth gets irradiated and we become mostly dead or perhaps mutants. That's right. Most mutations are not particularly wonderful, right? But every once in a while, you get a good mutation. A mutation that's survivable, that even aids, like gills, sure, or maybe like Wolverine's, his claws. I always wondered that. I don't know, though, because he's so pretty, it doesn't matter to me. Right? Right? And he can sing, I'm done. Yeah, I do have a lesson that I do with my lower level kids on, like, superpowers. It's kind of fun. With you guys? All right. Maybe I'll sing for you again on the last day. I'm hoping that maybe Nick will sing with me on the last day so we can harmonize. Excellent. I was wondering if you were working on that. All right. So here's the weird thing, guys and gals. Listen. Following this shift of the Earth's magnetic field, there's been basically mass extinctions that have occurred. Makes sense, right? Lots of radiation, and then lots of organisms die. Some don't, though. Some survive it. Like what kind of animals or organisms survive? Cockroaches. They are tough little suckers. Crocodiles, yes. Yes, some of the lower form animals, especially if... Stop yakking, please. Yeah. Those organisms that live underwater, of course, have that extra shielding. Water does a pretty good job of shielding and absorbing electromagnetism as well. But what's interesting about this is that after the mass extinction, those are always followed by an evolutionary bloom, so new organisms. So it's believed that, and we don't have real evidence because we can't just make the Earth's magnetic field go away, right? But it's believed that that irradiation did a couple of things. First of all, the extinction always equals opportunity, right? So if you create that opportunity, kind of wipe the slate clean, wipe the whiteboard clean, then there's all kinds of other organisms that come in and fill those opportunistic spots. They believe that it's possible that the dinosaur extinction, in part because it's timed with one of these shifts, may have contributed to it. There are lots and lots of scientific theories that point toward a big asteroid that probably block the sun for a long time, and, you know, reptiles don't do real well when it's cold, right? The last shift occurred approximately 50,000 years ago, and there was a new organism that came to being at about that time. Yeah, Homo sapiens. And you guys have probably heard of the missing link, right? The evolutionary theory that we were once monkeys. I love that one, monkeys. And that the monkeys got smarter and smarter, and then there's kind of like a hole, like, I don't know what's happening there. Oh, and then humans, right? There is a theory that says that we're just mutants, that we were taking advantage of the opportunity of that clean whiteboard, right, and jumping in to fill that. Now, I tell you this, and I also realize that this flies in the face of many religious accounts of the creation story. So I am not telling you how to think. I'm just throwing out some ideas, okay?